Okay, so today we are going to solve this problem. That will be the end of chapter 8. And we solved one problem last Thursday that could be the easiest problem that you can expect from this chapter. And this is the hardest problem you can expect from this chapter. So the problem that you will see, the vapor power cycle problem that you will see from the final exam is going to be between these two. So if you can solve this problem, then no worry about that problem in the final exam, okay? So let's focus on this one. This is the hardest one. It's a combination of everything. So we have a reheat process, ideal reheat process. So when you see this reheat process, the first thing that you need to do is draw this schematic for the reheat process. So we have a steam generator and we have two-stage turbine, high pressure turbine and low pressure turbine at the end. And we have a condenser and pump. So direction of the cycle is going to be from this steam generator to the high pressure turbine, from this high pressure turbine back to the steam generator, which is the reheat process, and then goes back to the second stage turbine. And then at the exit of this second stage turbine, we have a condenser and pump and steam generator. The inlet of this turbine is number 1. The exit of this high pressure turbine is number 2. The exit of this reheat process, which is the reheating in the steam generator, is number 3. The exit of this second stage turbine is number 4. The exit of this condenser, which is the inlet of the pump, is number 5. And number 6. On this on a TS diagram, for this ideal reheat process, you have 3 pressure values. The highest pressure between 6 and 1, and intermediate pressure between 2 and 3, and the lowest pressure, which is the condenser pressure, between 4 and 5. So I'm going to make 3 TS diagram. The highest pressure, intermediate pressure, and the lowest pressure. The exit of this steam generator is going to be superheat vapor, starting from here, maybe here, and isentropically goes down to number 2 and reheat in the steam generator, and isentropic expansion in the second stage turbine, and heat rejection in the condenser, and isentropic compression in the pump, and heat addition between 6 and 1. So there's number 1, number 2, number 3, number 4, number 5, and number 6. So whenever you see a reheat cycle, the first thing is to draw these two. And then there are 6 states. So you need to determine H1, H2, H3, there are 6 of them, H4, H5, and H6. All of them that you need to calculate. And to determine each H, you need to have at least 2 property values. So let's see. For H1, what do we have? Steam enters the first stage of turbine, which is number 1, at 28 megapascal. So P1 is 28 megapascal, and T1 is 520 degrees Celsius. And this steam exits the first stage turbine at 6 megapascal. So P2 is 6 megapascal. That's it. And it's going to be reheated in the steam generator at constant pressure. So P3 is 6 megapascal and to 500 degrees Celsius. That's the temperature after the reheat process. So number 3. So PT3 is 500 degrees Celsius. And we have an isentropic turbine efficiency, 78%, that we are going to talk about this later. And the pump has an isentropic efficiency, 82%. Okay. Now, the condenser operates at constant pressure. So the inlet of the condenser is number 4. The exit of the condenser is number 5. Both of them are at 6 kilopascal. So P4 is 6 kilopascal. P5 is 6 kilopascal. What about P6? That's the inlet of the steam generator, and this steam generator runs on constant pressure. So P6 is the same as P1, and P1 is 28 megapascal. So P6 is also 28 megapascal. By the way, one thing we know on this TS diagram, number 5 is saturated liquid. After the condensing in this condenser, the phase change process is going to be saturated liquids. That's the only thing we know from this TS diagram. So number 5, you can say it's a phase change process. Number 5, I'm sorry. Number 5 is going to be phase change process number 2, saturated liquid. So among these 6 H values, which one can we find? We know P1 and T1, so finding H1 is not a problem. We know P3 and T3, so we can find H3. We know P5 and it is a saturated liquid, we can determine H5. So let's find H1, H3, H5 first. According to this TS diagram, number 1 is a superheat vapor, number 3 is a superheat vapor, so we don't have to determine their phase change processes. So let's assume that they are superheat vapor and then determine H1 and H3. And H5, we know it is phase change process number 2, saturated liquid, so you can find H5. So H1 first, 28 megapascal and 520 degrees Celsius. You can go to table A4, superheat water vapor table. And 28 megapascal is right here. 28 megapascal and 520 degrees Celsius. H value is going to be, this one is a specific volume, specific internal energy, specific enthalpy, specific entropy. So specific enthalpy is going to be this number, 3,192.3. So let me write this value here. So from table A4, we get H1 3,192.3 kilojoule per kilogram. What about H3? We know 6 megapascal and 500 degrees Celsius. This one is a super vapor on this green. 1, 2, 3, 4, and 5. There is the number 3 for this phase super vapor. So you can go to super vapor table, 6 megapascal. Megapascal and 500 degrees Celsius. So the H value is going to be this one, 3,422. 3,422.2 kilojoule per kilogram. And last, saturated liquid at 6 kilopascal. H is going to be HF. H is going to be HF, which is the saturated liquid at 6 kilopascal. So HF at 6 kilopascal can be found from the pressure table. HF at 6 kilopascal, we have 151.53. 151.53 kilojoule per kilogram. So we found 3 specific enthalpy values. Now 3 more, H2, H4, and H6. So how can we find them? Unfortunately, we only know the pressure values at each H, P2, P4, P6. So we need another information. So what do we know? The isentropic turbine efficiency is 78%. What does it mean? What is isentropic turbine efficiency? How do we determine isentropic turbine efficiency? Isentropic turbine efficiency tells you how close your turbine compared to the ideal turbine. So to study and to compare these two turbines, isentropic turbine and the actual turbine, what you can do is that you can compare how much turbine power each can generate. So you are going to compare turbine power W dot T between two turbines. One is the isentropic turbine, the ideal turbine. The other one is the actual turbine. So between the ideal turbine and the actual turbine, which one produces more power? Of course, the ideal one. So whichever greater value goes to the denominator. So the power produced by isentropic turbine, I'm going to say S. Isentropic turbine goes to the denominator, and the actual turbine produces less power that goes to the numerator. So the actual turbine work goes to the numerator because we know this the turbine power produced by the ideal turbine is greater than this one. To have this efficiency value between 0 and 1, the greater value should go to the denominator, which makes sense. Now, how can we determine that turbine power? So I want to determine this turbine power. By the way, let's write power 2. So this one produces W dot T from high pressure stage. This one produces W dot T low pressure stage. This one rejects heat. W dot out. This pump consumes power. W dot P for the pump. And there is a heat transfer in between 6 and 1. Q dot in between 6 and 1. There's a heat transfer during the reheat process between 2 and 3. Q dot in between 2 and 3, right? So these are energy transfers between the surrounding and the Rankine cycle. 1, 2, 3, 4, 5, 6. By the way, we are looking at this high pressure turbine, and how can we determine the turbine power? We studied how to determine turbine power in a Rankine cycle. It's simply m dot times the difference in H. So it's going to be m dot times the difference in H. And what kind of H? For this high pressure turbine, there are two H values, H1 and H2. So whichever greater value goes to first, and the less value goes to the end. So between H1 and H2, which one is greater than the other? H1 goes in, some of this H is going to be converted to power. Then left over is going to be, the reject exits this high pressure turbine. So between H1 and H2, H1 should be greater than H2, right? Because this turbine power was a part of this H1, and that one has been removed from the turbine, so only leftover is going to be less than this one. So turbine power is going to be H1 minus H2. H1 minus H2. But this one is an ideal turbine, not the actual turbine. So I'm going to say it is not the actual H2, H2S. H2 when we have an isentropic turbine. Then what about, the turbine power by the actual turbine? The same thing, m dot H1 minus H2. So H1, both H1s are the same because that's the inlet of the turbine. The inlet condition does not change regardless of the turbine. Whether it is isentropic turbine or actual turbine, H1 doesn't change because that is determined by the steam generator. So this one is before entering turbine. So H1 is going to be the same. The only difference is that the exit of the turbine. Isentropic turbine will produce more power, so less enthalpy is going to exit the turbine. Actual turbine will produce less power, so more H2 is going to be, the exit this turbine. So H2 is the only property that differ between isentropic turbine and the actual turbine. Then what do we want to calculate? This H2 is going to be the specific enthalpy from the actual turbine. So this H2 is this one. So this is what we want to calculate. Then what do we know? The isentropic turbine efficiency is 78%, 0.78. And we can cancel m dot. Do we know H1? Yes, we know H1. This number, 3,192.3. Do we know H2S? If you can find H2S, you can determine H2. Then how can we find H2S? H2S is the specific enthalpy at the exit of an isentropic turbine. Isentropic turbine means entropy S remains constant. So how can we calculate this one? By assuming isentropic turbine. So isentropic turbine means P2 is 6 megapascal and S2 is going to be the same as S1. So this is how we are going to find H2S. Then do we know S1? Yeah, you can find S1 because we know P1, T1. So S1 can be found from the same table as we found H1. So let's go to 28 megapascal right here. And this is S. So what is the value? At 520 degrees Celsius, S is going to be 5.9566. So from this S1, let me write here. S1 is going to be 5.9566 kilojoule per kilogram Kelvin. So that is S2. Now we have a pressure and specific entropy. Then can you determine the specific enthalpy? Yes, you can. So let's do that. Now we have these two properties. Then how can you find H? The first thing is we need to determine the phase change process. Oh, can we assume that it's a superheat vapor? Not anymore, because we do not know. Because this one is the actual turbine. Now we are assuming that isentropic turbine. So let's determine the phase change process assuming isentropic turbine. To do so, we need to make a TS diagram. TS diagram at this pressure, 6 megapascal. TS diagram looks like this. To complete this TS diagram, we need to know T-set, SF, and SG. Where can we find T-set, SF, SG? From 6 megapascal. So let's go to 6 megapascal. Right here. Oh, that is not. That is a superheat vapor table. Let's go to pressure table. 6 megapascal is right here, 60 bar. So at 60 bar, which is a 6 megapascal, he said is 275. He said is 275.6. And SF is this number, SG is this number. So 3.0267, 5.8892. So we completed this TS diagram. So let's find this specific entropy on this TS diagram. We have 5.9. 5.9 is greater than 3.0, greater than 5.8. So 5.9 is going to be slightly right side of SG. So this number is somewhere here. So what is the phase change process? This one. 1, 2, 3, 4, 5. Superheat vapor. Phase change process. Number 5, superheat vapor. Then, to determine H, we need to go to superheat vapor table. So let's go to superheat vapor table at 6 megapascal. So now this one is slightly complicated. So we know the pressure is a 6 megapascal and specific entropy is 5.9. So we are going to find H value at this entropy. So 5.95 is greater than this one and less than this one. So between these two numbers. Then the specific enthalpy, H2S, that we want to calculate is going to be between these two numbers. So how can you find H2S? Linear interpolation. So you can do a linear interpolation between these two numbers to determine H2S. If you do, we get 2822.2. 2822.2. So write this one here. H2S is going to be 2822.2 kilojoule per kilogram. Okay? Then going back to this isentropic turbine efficiency. We know the efficiency is 0.78. We know H1, H1, H2S. We have everything but H2. Can you determine H2? Yes, you can. So this H2 goes here, and the value is 2903.6 kilojoule per kilogram. So we found H1, and now we have H2, and we have H3, then H4. So these are for H2. Now let's find H3. Oh, H3 is, we know H3, so let's find H4. How can we do that? We only know pressure, 6 kilopascal. So let's go read the problem statement. Each turbine stage, which is between 3 and 4, has an isentropic efficiency of 78%. So to determine H4, we have to repeat this process one more time. I'm pretty sure that you're not very happy, but that's what we have to do. So let me repeat this. You know, the isentropic efficiency equation is W dot by actual turbine divided by W dot T by isentropic turbine can be determined by M dot between H1 minus H2. Now it's going to be H3 minus H4. H3 minus H4. That is the turbine power from the actual turbine. Now we have an isentropic turbine. We know the inlet of the isentropic turbine is the same as the actual turbine, but the exit of the isentropic turbine is different. So I'm going to say not H4, it's going to be the different one, H4 of isentropic turbine. We know the turbine efficiency is 0.78, and we already know H3. They are, this H3 is going to be 3,422.2. So if you determine H4S, then you can find H4. So let's find H4S. How can we do that? T4 is 6 kilopascal. Do we know any other property? Yes. We assume that it's an isentropic turbine, so the specific entropy at number 3 should be the same as the specific entropy at number 4. So we assume that as 4 is the same as S3, and we can find S3 from where? From 6 megapascal and 500 degrees Celsius. So let's go to superheat vapor table and find 6 megapascal and 500 degrees Celsius. Where is S? This one. Entropy S. 6.8803. 6.8803 kilojoule per kilogram Kelvin. Now we have two property values at state number 4. They are pressure and specific entropy. Can you find H? Yes, you can. So how can we find H? We need to determine the phase change process. Oh wait, didn't we use superheat vapor? Yes. At number 3, at number 4, we don't know. So let's make another TS diagram to determine the phase change process. So TS diagram looks like this. And this is for 6 kilopascal. To complete this TS diagram, we need to find Tsat, SF, and SG. Where can you find Tsat, SF, SG from 6 kilopascal? So let's go to pressure table, water pressure table, and let's find Tsat 36.16. 36.16. SF 0.521. SG 8.3304. Now, the specific enthalpy that we know is 6.88. So let's find this value on this TS diagram. 6.88 is greater than 0.5, but less than 8.3. So our state number 4 is between SF and SG, right here. So this number is between SF and SG. So our process, phase change process is going to be number 3, saturated mixture. If you have a saturated mixture, you need to find another property, which is quality X, the ratio between liquid and vapor. How can you find the ratio? By using linear interpolation. So we know S. So why don't we use S? S4 is SF plus quality X4 times SG minus SF. Do we know S4? Yes, 6.8803. 6.8803. Do we know SF? Yes, 0.521. Do we know SG? Right here, 8.3304 SF. We just found 0.521. We have everything. Can we determine the quality X? Yes, we can. The quality X is 0.8143. So this one is 0.8. Oh, I said 8. 8143. So that's how we determine the quality X. Once you determine quality X, we can determine H4. H4S is HF plus quality X4 times HG minus HF. Do we know HF? We do not, but we can find them. from the property table at pressure 6 kilopascal, HF is 151.53. 151.53. Quality X is right here. Hg is 2567.4. HF again 151.53. So we have everything. Can you determine the quality X? I'm sorry. Can you determine H4S? Yes, we can. We have everything. So let's find this one. H4S is, do I have it? Yes, 2118.8. This one goes here. 2118 kilojoule per kilogram. Then we have everything. Can we determine H4 from this isentropic turbine efficiency? Yes, we can determine H4. Goes here. H4 is 2405.5 kilojoule per kilogram. And we have H5. So one more to go. We just need to find H6, and that's it. How can we find H6? What do we know? We know pressure, P6. But that's it. We need to have another property. What is it? Again, isentropic pump efficiency is 82%. Now we have isentropic turbine efficiency. So this one is for H4, now H6. Now we have an isentropic pump efficiency, not the turbine efficiency. The pump efficiency is here. Where should I write? Let's do it here. Isentropic pump efficiency can be determined by what? The same rule. We are going to compare isentropic turbine and actual turbine. For this isentropic turbine efficiency, for this isentropic pump efficiency, we are going to compare isentropic pump and actual pump. Then the question is, which is greater than the other between the pump power consumed by an isentropic pump and the power consumed by the actual pump? So think about this way. For the same pumping job, which one consumes more power? Of course, the ideal pump is going to consume the least power for the same pumping job, right? So between isentropic pump and actual pump power is going to be greater than the other. So this one goes to the denominator. So the actual pump, W dot P, actual pump goes to the denominator, and the isentropic pumping power, W dot P S, goes to the numerator. Then how do we determine this pump power? M dot times the difference in H. M dot times the difference in H. The pump, the inlet is 5, the exit is 6. Between H5 and H6, which one is greater? Of course, if you look at the direction of this pumping power, H5 goes in and pump power is added, and H6 comes out. So H6 is going to be the highest one. So H6 is greater than H5. So if you want to determine the pump power, it's going to be H6 minus H5, because the other way, you are going to get a negative pump power, which doesn't make sense. If you have a negative pump power, that means that pump is producing power. That would be great, but that's not happen, right? What about here? The same thing. M dot H6 minus H5. Wait, we have the same H6, same H5. That doesn't make sense. Between the inlet of the pump and the exit of the pump, what's going to change if you replace the actual pump with an isentropic pump? The inlet doesn't change, because there's nothing you can do if you change the pump, because inlet condition should be determined by the condenser. So whatever goes into the pump, nothing wrong with the pump. So if you replace the actual pump with an ideal pump, the exit condition is going to change, right? So what is the exit? Number 6. So H6 is going to be changed after you use an isentropic pump. So for this isentropic pumping power, H6 is going to be H6 of isentropic pump. And the isentropic pump efficiency is 0.82 according to the problem statement, and you can cancel M dot, and H5 has been found, this one, 151.53, 151.53. So we just need to find H6S to determine H6. Then how can we find H6? In the previous problem that we solved last Thursday, I gave you one equation and told you to use that equation whenever you want to calculate the specific enthalpy at the exit of the pump. That equation is H4 is H3 plus V3 times P4 minus P3. Of course, now the inlet is 5 and the exit is 6. So you're going to say, not this one, H6. By the way, this one is an isentropic pump. H6S is H5 plus V5 times P6 minus P5. Please make sure that you write this one on your formula sheet and use this equation. And do we know H5? Yes, we found it, 151.53. What about P6? The pressure, 28 megapascal. Are you going to use megapascal? No, kilopascal. 28,000. What about P5? 6 kilopascal. So if you find V5, then you can determine H6 of the isentropic pump. How can we find V5? Number 5, we have phase change process number 2, saturated liquid. So V5 is going to be Vf at what condition? 6 kilopascal. Can you find Vf at 6 kilopascal? Yes, if we go to the table, 0.06 bar, which is 6 kilopascal, Vf is going to be 1.0064. This is 1.0064 times 10 to minus 3 cubic meters per kilogram. So we have everything to determine H6S. This one goes here. Now, if you solve this equation, you get H6. Then this H6 goes here. What is the value of H6? 185.89 kilojoule per kilogram. That's how you determine H1 to H6. So whenever you have a vapor power cycle, such as Rankine cycle, to solve any problem, you need to determine the specific enthalpy value at each state. So in this case, we have an ideal recycle has 6 states. So you need to determine H1, 2, 3, 4, 5, 6. And once you determine all these 4 and 6 values, then you are ready to solve the problem. So this portion is for H6. Now let's solve this problem. What do we want to solve? We want to determine the quality of the steam exceeding the second stage of the turbine. What is the state exceeding the second stage turbine? So this is the second stage turbine exceeding the second stage turbine, number 4. So we want to determine the quality at number 4, which is X4 is the first question. Then you may have a question. Didn't we find X4 already? Not really, because this X4 is for an isentropic turbine. This one is an actual turbine. So you need to recalculate that X. Then how do you determine this X? Now we have H value. This H4 is going to be HF plus quality X4 times Hg minus HF. Then do we know HF? You can find that HF at what condition? 6 kilopascal. So what is HF at 6 kilopascal? It's written here. We already found 151.53. Hg here 2567.4, 151.53, and the specific enthalpy is going to be this value, 2405.5. So we have everything. Can you determine X4? Yes. X4 is going to be 0.9330. So that's how you solve this problem. Now, that's not the end of this problem. The second part of the problem is you need to determine the thermal efficiency. So how do we determine thermal efficiency? Desired output over required input. What is desired output? The net power you can produce over required input. You need to provide heat. So what is the net power in this ideal reheat cycle? How many powers do we have? Turbine power, number 1, turbine power, number 2, and pump power. So there are 3 powers. 2 are the ones that we produce. 1 is the one that we consume. So this is going to be the one that we produces. The turbine power from the high pressure turbine plus turbine power from the low pressure turbine minus the pump power divided by how many heat transfer into the Rankine cycle. One between 6 and 1, the other between 2 and 3, these two. So Q dot in between 6 and 1 plus Q dot in between 2 and 3. Then, can you solve it? Yeah. how do you determine this turbine power? The high pressure turbine is right here. The inlet is number 1, the exit is number 2. The turbine power can be determined by m dot times the difference in H. Always the same rule. M dot times the difference in H. Then how do we find whether it is H1 minus H2 or H2 minus H1? Of course, this turbine power should be a positive value. Between 1 and 2, 1 goes in, reproduces turbine power, and leftover exits. So 1 should be greater than 2. So this is 1 is going to be H1 minus H2. What about low pressure turbine? This one, low pressure turbine. The inlet is number 3, exit is number 4. Number 3 goes in and reproduces power, and leftover is going to exit number 4. So H3 should be greater than H4. H3 minus H4. Then minus the pump power. The inlet of the pump is number 5. The exit of the pump is number 6. So number 5 goes in, and pumping power is added. Altogether exits at number 6. So number 6 should be greater than number 5. H6 minus H5. Divide by Q dot between 6 and 1. M dot times enthalpy difference. Between 6 and 1. 6 enters this steam generator, receiving heat, and altogether exits at number 1. So number 1 should be greater than number 6. H1 minus H6 plus Q in between 2 and 3. Q goes in, and Q in enters this steam generator. Both of them exits at number 3. So number 3 should be greater than number 2. H3 minus H2. So you can cancel everything, m dot, m dot, m dot, m dot, m dot. We know H1, H2, 3, H4, H4, H3, H5, H6. So we know all the H values. Can you determine the efficiency? Yes, we can. I don't know the answer, by the way. So this is how you solve an ideal reheat cycle, the hardest one. So how can you prepare for the final exam? Solve this one. If you can solve this problem without any help, of course, you may need to, to go through and watch my lecture, the video, etc. Keep practicing. And if you solve maybe 5 times, you may need any help. You may not need any help. Then when you go to the final exam, that problem is going to be super easy. Okay? Of course, this problem takes a long time because we have 3 isentropic efficiencies. Of course, in the final exam, as you expect, there won't be 3 isentropic efficiencies. Maybe 1 or 2, but most likely 1. So if you can do 1, then it may not take this much. So it should be done within 15 minutes. Because my original plan is that 4 problems for 1 hour. So you can spend 15 minutes per problem. So I will do my best to, to make sure that you can solve each problem average 15 minutes. So that completes chapter 8, vapor power cycle. Any question? Okay, and we have 11 minutes. No? Oh, it's at 2:54. We have 21 minutes. So let's talk about the last chapter of this class. Gas power systems. In this gas power systems, we are going to study 3 cycles. The first one is Otto cycle. That is gasoline cycle. Not the movie, the guy called Otto. There was something like that, no? Tom Hanks was the old guy, hate everybody nearby, right? You didn't watch that one? Okay. So the Otto cycle is the first one we are going to study. And the second is diesel cycle. And finally, gas turbine, Brayton gas turbine. Okay, so 3. Then what we are going to do? Are we going to learn every detail of each Otto cycle, diesel cycle, and gas turbine cycle? No, this class is not Otto cycle or diesel cycle. This class is thermodynamics. So we are going to briefly go over each of them, and we are going to study how we can, analyze each cycle thermodynamically. So thermodynamic calculation and designing each Otto cycle and diesel cycle is what we are going to do. Okay. To do so, we need to we need to briefly go over some characteristics about Otto cycle and diesel cycle. So we are going to study Otto cycle and diesel cycle first, then gas turbine later. So Otto cycle and diesel cycle are also called spark ignition cycle and compression ignition cycle. So we are going to, see, the difference between these two. This one is Otto cycle. Otto cycle is the gasoline cycle. The engine, in your car, most of diesel is, on the other hand, compression ignition. So let me give you the main difference. The main difference is that both of them have a similar piston cylinder device. So what we do is that we are going to have another gas in the piston cylinder device, and they will undergo a compression that will increase the pressure and temperature inside this volume. Then what's going to happen? It's going to push this piston downward. That's how we are going to produce this shaft power. Okay. Then, how can we, induce the combustion inside the piston cylinder device? There are 2 ways. One, we can have a simple spark plug that will ignite, whatever the fuel and air mixture. That is Otto cycle, spark ignition. So you have the spark plug on top of, each engine. If you have 4-cylinder, there are 4 spark plugs, 8 cylinders, 8 of them, simple. On the other hand, the other one is we are going to increase the pressure and temperature of the fuel and air. Then what's going to happen? Because of the high pressure and high temperature, it's going to self-ignite. So that is compression ignition. Then what is the main difference? Spark ignition system is simple. You just need to have the one spark. And then once we compress air-fuel mixture, then the spark is going to ignite the fuel and air mixture. There's a combustion, and it's going to push the piston downward. So that's how we are going to create this shaft power. It's simple. But one thing that you can think of is going to be, if you have a combustion within this volume, what about if you have a same combustion within a much smaller volume? Which one will create more power? When you make it as small as possible and let them ignite, then the combustion, the power produced by the combustion is going to be much greater, right? So ideally, we want to compress this air-fuel mixture as much as we can. So in other words, we want to increase the compression ratio. What is compression ratio? The volume inside the piston cylinder device when the piston is at the bottom, at the center, which is when it is the lowest position. That is the bottom, at the center. When the piston is at the uppermost position, that is called top, at the center. So the volume ratio between when the piston is bottom dead center divided by the volume when the piston is at the top dead center, that is called compression ratio. So simply speaking, as you understand, if you pressurize the system as far as we can, and then let them undergo combustion, that's when we can produce the maximum power, right? So we want to increase the compression ratio as much as possible. Then now let's do that on this spark ignition system. In this spark ignition system, we have an air-fuel mixture. So we are going to pressurize it, and at a certain point, the pressure and temperature may be too high. So before this piston goes to the top dead center, there may be the combustion. Then while it is going up, oh, it comes back. Is it okay? No. So the wheel is going to go up, and there's a reverse, going up, reverse, like that. So we don't want that to happen. So what the problem is that if you compress more, the temperature and the pressure inside the piston cylinder is going to dramatically increase. So when there's a fuel inside, it's going to the self-ignite. We don't want that to happen. We want to increase the compression. What can you do? We can just add air in the system without fuel. Can we do that? Yeah, we can do that. We can just insert air in the piston cylinder device and compress it up as much as we can. And when it is at extremely high pressure, extremely high temperature, then we can inject a fuel. Then because of the high temperature and high pressure, we don't need the spark plug. It's going to self-ignite. That is compression ignition. That is the diesel cycle. So there's no spark plug in a diesel cycle. So we can compress a lot. So the power output is going to be much greater than spark ignition. So that's why when you drive a sedan, it's most likely the gasoline engine, which is Otto cycle, spark ignition. But if you drive dump truck, gasoline powered dump truck, not really. Most of them are diesel powered. Why is that? Because we can compress more, so you can produce the high, higher power. So diesel engine is usually preferred for high power applications. On the other hand, the spark ignition is going to be for low power. It's not an advantage. Then what is the problem of this diesel engine? You need to compress this air as high as possible. Now you're going to inject fuel at extremely high pressure, extremely high temperature. Do you think it's going to be easy? No, it's not easy. So that's why usually diesel engines are more expensive than gasoline engines. So the good thing about, so let's talk about the pros and cons of each, the cycle. Spark ignition system is cheap because it's simple. You just need to, we have a fuel and an air. Let them mix them, and then add into the the engine, and then let the spark plug ignite them. So nothing wrong. Very simple, straightforward. On the other hand, diesel engine is complicated. So usually lightweight and relatively low cost, the application, we use gasoline engine. And for, the high power applications, and when we use diesel engine, the compression ratio is very high. For the same combustion, you can produce more power. What does it mean in terms of economy? It is high. It has higher efficiency. So usually diesel engine has higher efficiency. So when fuel economy is required, we use compression ignition. So when you drive a sedan or SUV, most of them are gasoline engines, right? Spark ignition. But what about when do we need high power and the fuel economy, high fuel economy. Like, those machines, in the construction business, or when you drive, the container ships. We don't care about how fast this container ship, the sails. We don't care. We only care about the cost, right? So in that case, we use compression ignition. Okay. Then, is that the only difference? So sounds like, except the low cost, everything is good about in terms of diesel engine. Is that right? There is another thing that we need to consider. If you only talk about, the energy conversion point of view, the diesel engine might be more beneficial because it has a higher efficiency. You pay less fuel, and then you produce more power. But there's also a downside. When we use an Otto cycle, we have an air-fuel mixture, and this fuel is usually consists of carbon and hydrogen mixed together. Like a propane is 3 carbons and 8 hydrogen. Octane, 8 carbons, and I don't remember how many hydrogens there, but typically, the fuels consist of carbon and hydrogen. So when you have a combustion, this carbon becomes carbon dioxide. Hydrogen become water. So nothing wrong. But if you have a diesel engine, the combustion takes place at extremely high pressure because that's how we increase the efficiency. When combustion takes place at extremely high pressure, air is not just pure oxygen. Air has about approximately 80% nitrogen and 20% oxygen. Nitrogen is usually considered as an inert gas, which means that it's not going to react. But at extremely high pressure, it's going to react. So usually diesel engine, at this extremely high pressure, this nitrogen is going to react with oxygen. Then what we produce is air pollution. And that's why, you remember that all the diesel gates about years ago, when the European automobile companies are lying about their, the exhaust gases. Those are the problem is that the high pressure. So technically, when you use a diesel engine, because of the advantage of having a diesel engine is high compression ratio. That gives you higher fuel efficiency. But that has a downside, which means that air pollution. So there's no clean diesel engine. Diesel engine always comes with fuel economy and air pollution. So it's more like, the balancing, do we need to consider, the energy saving or, the environmental friendly? So we need to balance that. There's another thing, compression ratio. So for the same, the engine room, so for the same piston cylinder device, one can be, let's say that this one is about, the 6-liter engine. Then one engine can be this big, and the other engine can be this big. This one is 6 liters. This one is also 6 liters. So both of them have the same displacement volume. So do you think that they produce the same power? This is just for your information, not a subject of thermodynamics. Just trying to give you some information that's fun to know. So this one is a 6 liter. This one is 6 liter. Sounds like they will produce the same amount of power, but not likely. So here, when you talk about compression ratio, this one compresses more, right? So if you have solar, the diesel engines, you can increase the compression ratio, so their fuel economy goes up. Then, is this always bad? No. Think about, the RPM point of view. How long it's gonna take for a piston to move from the bottom dead center to the top dead center. It's going to take a long time. What about here? Very quick. So if you use this engine, the RPM can go up dramatically, simply. This one, no, it stays very low. So when you drive a racing car, usually racing car RPM is pretty high. So each time you can provide power. So providing power is going to be more frequent. On the other hand, this one is like a one kick and with a long time and another kick. So in this case, it gives you more fuel efficiency. But if you think about the high the power demanding situation, this one is more preferred. So you use this taller engine when fuel economy is the most critical factor. When high power output is more critical than you use this type of engine for the same capacity. That's why when you watch some movies about container ship or submarines, diesel engines looks pretty tall. Why is that? We want to increase the compression ratio so that we can have much lower fuel and much higher fuel efficiency. So usually container ships or anything that runs slow, steady, we prefer those taller engines with high compression ratio. On the other hand, when we prefer the high the power application, we don't care about the efficiency, then we usually have this thicker the cylinder have more frequent the strokes. Just for your information, okay? So we get the idea about what is a spark ignition system, what is compression ignition system, and what is the good thing about spark ignition, and what is the advantage of compression ignition system. So how can how they run? There are 4-stroke cycles and 2-stroke cycle in general, and in this thermodynamics course we are going to focus on 4-stroke cycle, which is most widely used. So when you drive your car must be the 4-stroke cycle, unless you have a Tesla or something, or if you have a bike or the lawn mower, they are usually 2-stroke cycle. So let's briefly go over this 4-stroke cycle. So it is always easy when you understand the figure of this the piston cylinder device. So let's just start with the initial state of this compression process. So we assume that the piston is at the bottom dead center. The piston moves downward. We have a large volume inside. It's going to be filled with a mixture of air and fuel. So what do you want to do? Do you want to have a combustion right away? No, we want to increase the we want to compress it as much as possible so we can produce high power. So that is called compression stroke. So we are going to move this piston upward. So the volume goes down and pressure goes up. This one is PV diagram. PV diagram. So volume goes down and pressure goes up when you move this one. That is called compression stroke. Once it reaches the top dead center, then the spark plug is going to induce combustion. So what's going to happen? So there's a combustion occurs, pressure goes up and temperature goes up dramatically. So what's going to happen is that whatever the gas inside is trying to expand. So it's going to push the piston downward. When pressure goes down and volume goes down, that is called power stroke. That's when we produce power. Then once it reaches the bottom dead center, what's inside? Air-fuel mixture? Not anymore. We have an exhaust gas. We want to get rid of it. That is called exhaust stroke. So we are going to move the piston upward, and with this expansion, exhaust valve is open, so we can remove this gas at constant pressure. And then this piston moves downward when intake valve is open. That is called intake stroke. So fresh air-fuel mixture goes in. Now it goes back to the initial stage of compression stroke. So that's what happens. Okay. One minute. So that's a four-stroke cycles. Smaller engine prefers two-stroke cycles, so which is much more simple. However, it has a disadvantage, which is since we are combining three the strokes together, so it has less efficiency. But of course, it's a small engine, so efficiency is not that much important because the actual fuel consumption is way less than the big size engines. So the last one is the mean effective pressure is an important performance parameter. So when you have a higher mean effective pressure, you get higher, the power, greater, the net work you can produce, which is, the related to smaller engine and shorter engine. Okay, so that's the background information, and based on that, we are going to introduce how we can apply thermodynamics equation to understand these two cycles after Thanksgiving. Okay, that's it, and see you next week, and happy Thanksgiving. Oh yeah, sure, take all. $10 per page.